Welcome to the project demonstration of power factor correction of EV charger using bridgeless isolated Zeta-Luo converter. So the main application of this project is by making use of this Zeta-Luo converter, we are going to making the power factor correction while charging off a battery. So if we are not corrected this power factor, then there is a loss of power while charging off a EV vehicle charger by EV vehicle battery. And then due to that power losses occurred and we will get the energy loss in that. So in order to eliminate the power losses, we are making use of this power factor correction using the Zeta-Luo converter with help of this circuitry. So here this application is done with help of these two MOSFETs mainly used along with the two inductors, coupled MOSFETs and coupled inductor, and there we are going to get in the triggers pulses from the microcontroller while continuously monitoring that through this ESC. And whenever the fluctuations occurred, we are going to switching that with the help of these two MOSFETs to neutralize the ripples, and there we are going to maintain the current and voltage waveforms in the same manner so that we will get the unity power factor. And while the output is directly given to the battery pack through this LM2596 voltage regulator. So we are using this regulator to charge a battery by regulating the voltage up to 12.5. So with the help of this Zeta-Luo converter along with LM2596 voltage regulator, we can increase the voltage up to 120 volts of DC power supply, so that in real time we can charge up to 120 volts of battery pack also. So there we are going to use the lithium ion battery pack of 12 volts. Generally it is 11.1 volt, as 3 lithium ion batteries are connected in series, so we'll get 12 volts around, and each battery is of 3.7 volts with 2600 milliamp of current can be generated from this one. So here we are providing the 230 volts AC input to the circuitry. So there with the help of this circuit directly we are going to convert the AC to DC, and with the help of filters we are going to get the regulated voltage without using any rectifier, bridge rectifier, as here we are not going to use the bridge rectifier or off bridge rectifier. With the help of capacitive and inductive filters, we are making use of this circuit to convert the AC signal to the DC signal, and these two MOSFETs will act as a converter circuit. Means whenever the negative waveforms come to the picture, then these MOSFETs will convert the negative current to the positive current. Means it will allow the negative current to pass the output voltage, and there with the help of these inductors, these two transformers, we are making use of them as inductors and the capacitive filters. There you can see the minute inductors also, which is of 100 microhenry. This is the 250 microhenry of capacitance of inductors we are going to use, and these three capacitors for filtration purpose. So once the voltage got filtered after this Zeta-Luo converter, the output is given as input to the LM2596 voltage regulator, and output of that is input to this our battery pack. And while we are charging the battery, there is a chance of MOSFETs getting heat up or inductors may getting heat up. So in order to eliminate that, for safety purpose, we have provided this secondary source to charge a battery. So for demonstration, while the project is demonstrated directly, we can use this battery pack charging through this Zeta-Luo converter, but in normal time we can charge a battery pack using this transformer circuit, as we can't make this continuously, as the chance of getting heat up, so nothing will happen to that, but it's getting heat up in some times due to the battery consumption more directly. It will ask for the more voltage to charge the battery. There the charging time either from this Zeta-Luo converter or the transformer will take around 2 to 3 hours to be fully charged. Till the duration we should keep the battery charging either through this Zeta-Luo converter if the MOSFETs or inductors not getting heat up, or else you can use this secondary source to the charger battery. So let us see the demonstration, and let us see this electronic speed controller is connected at the pin number C3, and A4 A5 pins are connected to this MOSFET switching purpose to convert the AC signal to the DC pulsating DC, and the inductors will convert that pulsating DC to pure DC voltage, and there we are regulating that, as we can get around of 18 to 25 volts from the Zeta-Luo converter. So in order to regulate that to the pure DC of 12.5 volts, we are making use of this LM2596 voltage regulator, as the battery operating voltage is 11.1 is the battery voltage and charging voltage is 12.5 maximum. So in real time, as we discussed, we can go up to 120 volts by eliminating this and by regulating the signals into these MOSFETs. There we will get the maximum of 120 volts of pure DC voltage with 2 amps of current can be generated directly from this Zeta-Luo converter. As you can see this, you get switched on and this is on off switch. So initially beeps will come from this BLDC motor, then automatically will start rotating with the help of this battery pack directly to this BLDC motor. So the main concept in this project is directly right. So see once again. Right, it starts directly to run the BLDC motor. So the main application of this project is to charge our as we are running it directly battery pack only. There is no power supply. This only power supply given as input to the battery charge circuits. And while we demonstrate in the project, you are not supposed to allow to touch any component on this board, as we are dealing with the 230 volts directly input to this circuits. Right. So finally, the major components in our project is we are reporting the dual CC inputs to the Zeta-Luo converter, which is a bridgeless isolated Zeta-Luo converter. Means without using of any bridge rectifier, we are going to convert the AC to DC, and then based on the required voltage to charge our EV battery charging circuits, we are regulating that voltage to the required voltage. Now we are going to regulate that to 18 to 25 volts, and after that we are regulating that to the constant of 12.5. So there we can see one more question is we can raise that. Why can't we control the directly output voltage from this Leo boost converter to 12.5 only? As if we regulate the output voltage of this Leo boost converter to 12.5 only instead of LM2596, there is chances of voltage fluctuation. That's why we used to say that it is going to be the 18 to 24 volts of voltage. It's a variable voltage. So there we are going to use that. Means we keep the voltage output of this Leo converter to the 18 to 25, and we regulate that to the required voltage of 12.5. If the voltage drops also to 16 to 15 volts, but this will regulate that to 12.5 constant output voltage to charge a battery pack. Same thing for higher battery voltages, whether 48 or 60 volts. So like then real time we can utilize this project.